Good morning, everyone. Well, we're getting to the latter part of our study with the logs and exponents. That goes a lot quicker than the first part of the course. And what we want to do today is to continue with the identities that we introduced, say some more about those and see how those actually work to manipulate logarithmic and exponential expressions, and then segue into some work with equations. That is, we can solve some very straightforward equations using the definition of the logarithm, but I want to point out some ideas that will make our solution of equations a little bit more interesting, and then also using these new identities to help broaden what we can actually do. Even though we don't have the use of the calculus to study logarithms and exponents, that is, we're preparing for that, everything that you learn in this class you will carry with you and you find to be very useful. The good thing is that in calculus, even though the initial work will seem very odd compared to what we're doing now, it will turn out that everything we've talked about is consistent. That is, all the things that you learn in this class about logarithms and exponents, all these things are actually true. It's just that when you introduce the natural logarithm as an integral, it seems very foreign compared to how we've done it in this class. But that's the pre-calculus method. And then we'll see that the pre-calculus method and the calculus method actually come together, and that the work that we do is consistent, and that we will use both adaptations to come to a better understanding of the types of problems that we're going to be doing. Now, what I want to do first is to share with you what we basically talked about yesterday, and then go through some examples and do a couple of very simple proofs of this. I just wanted to showcase 3 items. One is new, but these 2 items here we actually talked about yesterday. That is, we had the power rule, and the power rule is very, very flexible. For instance, x can be fixed. This could be exponential, and the r can vary. I mean, we have all kinds of flexibility here, or this can be just a plain old power function. What is nice about the power rule is it allows us to move this power to a coefficient of the logarithm. So that in and of itself is a very remarkable characteristic of the logarithm, of the base A logarithm. And we want to talk a little bit more about that. Now, I did mention, and the last part of the theorem that I listed was the change of base. That is, we have a base A logarithm that we want to change to base B, and we talked about how the formula is not too difficult to remember. You change to base B just in a cosmetic way, and then you have the change of base factor in the denominator. That is the base B logarithm of A, where A was the old base, so to speak. Now, I did want to make one comment, and this is a very important one, though it doesn't really require a theorem. If we want to change bases with exponential functions, it's just very simple. It's using the inverse relationship between the logarithm and the exponent. So if we have a to the x and we want to change to b to the x, we're just taking basically the base b logarithm of a to the x and then bringing the x down in front using the power rule. So changing the base in an exponential function is actually simpler than doing this. They are related because these are inverse functions, but this is so easy it doesn't even require a theorem or any kind of motivation. But the reason I want to speak of it is because in calculus, we focus on the natural base, that is the E base. So if we have a maybe 10 to the x or 2 to the x, we can convert to the natural base this way using this theorem, where again we replace b with the natural base. So this kind of structure here is what you spend a lot of time on in calculus. That is, E is the base of calculus. It's like the number pi is the number for the geometry, because when you have the ratio of the circumference to the diameter of any Euclidean circle being pi, then obviously you can't get away from that. So again, I just want to make you aware of the fact that all of these items that we're working on now, we will use often in calculus, and their forms will not change. That is, these will be exactly what you're going to use in calculus. So a lot of the items that we discuss here are directly transferred. What's going to happen is that we're just going to add new items to the list to basically build your foundation and make you more adept at working with these. Now, what I want to do is to write down in our pre-calculus way some justifications for these rules. Now, what that means is that we can use what we already know about the logarithmic and exponential functions and not have to worry about the fact that we don't know any calculus. In our limited way, we can actually effect a proof if we utilize what we know about the base A exponential. So that's really the kink that we have here that allows us to move forward in a positive way, I'm saying. In calculus, we'll actually get all of these rules by just dealing with the natural log, but that will be something we'll do at the next level. So let's go ahead and write this down. So we have the base A logarithm of x to the r equals r times the base A logarithm of x. That's the power rule. So what we can do, we'll say, why is this true? I mean, with what we've done so far, can we illustrate why this is actually the case? And we can do it. So what we're going to do is we're going to let z be the base A logarithm of x. The whole idea here is that we define the base A logarithm to be the inverse function of the base A exponential. So the logarithm is a power of the base. So every time we write this, we automatically have the following. That is, the power of A that equals x is z. So we say x equals A to the z. That's how we define the logarithm. We define it through the base A exponential. When we solve equations, we're often quoting this. And this mechanism here is what you must understand. And if this is not clear, then your understanding of the logarithm is limited. And we don't want that. We want this to be clear. So when you sit down to do any work with logs and exponents, you should write this down first. That is, it will always be the way to understand the process of taking logarithms and converting between the two forms. Now what we can do is we can use the laws of exponents. That is, x to the r will now be a to the z raised to the r. So with the use of the exponential rules, we're in good shape. So we have z times r. So this is a to the z times r. Or if you will, we can just write the r first, like that. Okay, just using commutativity. Now, this is where we're in good shape, because now we basically have a logarithmic equation, an exponential equation, and now we can take base A logarithms. What's the equivalent of this? Now, the base A logarithm of x to the r, which is what we want, will now be the base A logarithm of a to the rz. Now, this is what we like when we work with logarithms. That is, the power of a that equals a to the rz is rz, because the input or the argument is already a power of the base. So what's the logarithm? Power of the base. So we get rz. And then, of course, r is r. And z is, as we've defined it, the base A logarithm of x. So based upon how we have set up the logarithm, base A logarithm, as the inverse of the base A exponential, it is true that we can actually move the r to the coefficient. That is, the r now, the power, can now become a coefficient of the base A logarithm. And of course, the beauty of this is that we can go in the opposite direction. We can go here to here, and then we can reverse it here to here. That's one thing that students often have issue with. You have to be flexible in both directions. That is, we think about combining logarithms and we think about expanding. And in calculus, there'll be reasons to do both. Solving equations usually allows us or requires us to combine, whereas if we're differentiating logarithmic functions, it's better to expand, just because our procedure for differentiation will actually be easier. So again, it always depends on the context. Now, the other one was the change of base. Let's write that down. So say we were interested in writing the base A logarithm in base B. So we have the base B logarithm of x divided by the base B logarithm of A. Why is this true? Again, can we effect a proof of this? And this actually will be a good enough proof for here and forevermore. I mean, this basically just, again, relies upon the same theory. And we don't need to change this when we get to calculus. The idea in calculus is that we will be able to prove the logarithm identities just by using properties of the logarithm and not having to use the exponential. So again, you're thinking, you don't have to worry about it. All of these rules will stay the same. You're just going to get added information. So now we're going to do the same thing that we did before. We're going to I'll just let y equal the base A logarithm of x. And of course, then we're going to want to take base B logarithms to introduce the base B. And so it's not very difficult when you think about it. You do what you have to do to get the formula. But now, just like in the previous deduction, what's a logarithm? It's a power of the base. So the power of A that equals x is y. So x equals A to the y. This is even easier than the last one. So now what we can do is take base B logarithms. So when we do that, that's easy to do. So now we look here and we have base B logarithm of x equals, in this case, the base B logarithm of A to the y. So we take this equation and we take the base B logarithms. And now notice we can use the power rule. So we have the base B logarithm of x equals, again, this works for a fixed base. This is true for all bases, if fixed or variable. And so the y can come down as a coefficient. So we have y base B logarithm of A. And now we can solve for y. So y equals the base B logarithm of x divided by the base B logarithm of A. But of course, y is the base A logarithm of x. So this is kind of like, smoke and mirrors, so to speak. We say the same thing over and over, but what we're seeing here is that in order to get a proof, or at least some reasonable steps, deductive steps to show this valid, we have to use the power rule. So what we're seeing here is that not only do we have the definition of the logarithm, but we have to use the fact that this identity helps us to prove this result. So again, in mathematics, we're forced to make sure that everything is consistent. That is, if we don't have consistency, then we might not be able to utilize a particular result. And if it doesn't work seamlessly throughout what we're doing, then we may have to discard it. But we don't have to discard any of these. And you will, as you continue in pre-cal and then on into the calculus sequence, use the identities and the properties of the logarithmic functions here and forevermore, so to speak. And then as you move into other engineering math classes and other math classes, they will continue to be a part of your background. So I wanted to make sure that you at least understand how we are defining the logarithm. The logarithm is a power of the base. So that power is the logarithm. That is, that exponent is the logarithm. So what we want to do is maybe look at some of the examples that we have that basically discuss some of the ideas with the identities. So let's look at that. So what I find is that students don't really appreciate any of these identities until we start solving equations. But just so that we don't feel like we've been pushed into the deep end without a life raft, let's do a couple of examples first. So example. So in the WebAssign, we might be asked to evaluate an expression. And of course, all evaluations, all mathematics are assumed exact unless directed to approximate. So that is the unwritten law in WebAssign and in mathematics generally. It shouldn't be the case that I have to tell you that the exact answer is the mathematical answer. Somewhere down the road that got lost. And I'm here to tell you that we have to accept that again. We have to be ready to give the exact answer. We've just gotten lax. So we have the base 2 logarithm of 70 minus the base 2 logarithm of 8 minus the base 2 logarithm of 35. So the idea is we don't want to just run to our Google calculator and use change of base to compute this. Even though it would give us the same answer, it's not what we want here. The idea is we want to use the calculator when we need an approximation because it's beneficial for our work. If we've gotten to the end of a problem and we have a client that needs a decimal approximation. Otherwise, we need to use the mathematics that we know. So first, what we're going to do is we're going to leave this alone and we're going to pair it with this term with the minus and think about using the quotient rule. But for right now, we're just going to write them beside each other. So we're going to reassociate by using the commutative law. These are all real numbers. That is, this is the power of 2 that equals 70. This is the power of 2 that equals 8. And this is the power of 2 that equals 35. But this is easy here. We first observe that 8 is just the third power of 2. So that's easy. This would just be minus 3 because 8 is a power of 2. What is the power? 3. What's the logarithm? The power of the base. So we say the base 2 logarithm of 8 equals 3. So we just replace that term with 3. And now, of course, we have the difference of 2 logs, which is the quotient rule. So we can combine these two. That is, here's the numerator and here's the denominator. So we want to write this as a fraction. So the base 2 logarithm of 70 divided by 35 minus 3. Now, of course, 70 divided by 35, well, that's just 2, very simple arithmetic. So the base 2 logarithm of 2 minus 3. But the power of 2 that equals 2 is 1. So again, a very simple calculation, 1 minus 3, and we get negative 2. So what we want to notice here is that there'll be many, many examples where you are asked to evaluate. Maybe you're solving an equation and you give an exact answer. And then WebAssign in the next step of the problem will say, please give an approximation. So in many of the problems that you'll have with the equation solving, that format will be what you will expect. Again, the exact answer is always the goal. And then use that exact answer to effect a good approximation. For instance, when you're doing the finance problems, do them the way I've taught you so that you work and generate an exact answer, and then you have no round off error. The problem with putting in decimals and being careless is that it ruins your calculation, and we don't want that. So make sure that you always strive for an exact calculation. Now, one other example here might look like the following. That is, we want to expand. Now, you might think this is just silly stuff. That is, why do we just want to use these rules to expand? Well, later on in calculus, you'll see a very great use for this. Right now, just look at it as an academic exercise. So we have the natural log. Remember, the notation for the natural log is the ln. You think maybe we should write it NL, but ln has stuck. And we have a quotient R divided by 8 times S. And we want to expand this. Very simple problem. Well, now we're thinking, okay, well, we have the quotient rule, so we'll have the log of a difference. So we'll say the natural log of R minus the natural log of 8 times S. And then, of course, this is fixed. We can't do anything with this, but this is a product. And so we can use the product rule. So now we have the natural log of R minus, and we'll use our parentheses because we're going to want to distribute the minus here. We'll have the natural log of 8 plus the natural log of S. So remember, the log of a product is the sum of logs. The log of a quotient is the difference of logs. So expanding is where we produce more log terms, which again can have a positive effect depending on the context. And so now we just distribute the negative. So we have the natural log of R minus the natural log of 8 minus the natural log of S. So think of this as a symbolic calculation. Again, the natural log of 8 is a number, but it's not a nice number. It's the power of the natural base that equals 8. So that's an irrational number. And these are just variables. So these are symbolic. So again, doesn't matter on the order that you type these. It just makes insistent sense that this has a negative and this has a negative. The order, of course, being immaterial. So when it comes to writing or expanding, right now, just think of this as an academic exercise, thinking this is giving me an opportunity to practice the techniques that we learned in college algebra. Now, maybe another example that's actually useful to what we're going to be doing is called the combine example. So say, for instance, we're solving an equation and we have several log terms. We need to combine them so we can use the definition of logarithm. Remember, the definition of logarithm requires that we only have one logarithmic term. So we would need to combine to make any effort to use that realizable. So here's an example from your WebAssign, and it looks like this. We have two. Now, there's no preference here for the natural log. The natural log just comes up a lot, and maybe it's good that you get used to it for calculus. Plus 5 times the natural log of x Then we have minus 1/2 the natural log of the sum, x plus 7. Notice a lot of times, if I've got a fraction or a product, Weber sign will always stick in the parentheses, but here this is very clear. But when we have sums, it's not clear unless you use the parentheses, because we want to make sure that you know that the argument of the natural log is the sum of x and 7, where here the argument is clear, it's that fraction. The argument here, when we look at, where did I write it? Right here, is that product. Juxtaposition is always fine algebraically, but sums, when we're applying a function, we do have to use the parentheses. So be careful in that when you're working with your pencil and paper. So now if we want to combine, we're thinking we need the power rule to go in the backwards mode. So the 2 needs to become a power of the 2. The 5 needs to become a power of x. And then of course we can just take the negative 1/2 up, and that can become a power of the x plus 7. So let's do that. Use the power rule in reverse, so to speak. So this will be the natural log of 2 to the 2nd power plus the natural log of x to the 5th power. Now, of course, students will say, well, do I use the 1/2 or the negative 1/2? Will it matter? And of course it won't matter. But we'll just go ahead and do the plus and just take the negative 1/2 up to the power, just to get some practice with this. Again, if it did matter, then our result would not be any good, because this is legitimate. If we want to take the negative with the coefficient, that's fine. If you don't do it, it will not change the result. So now, first, we look at this and say, well, you know, we can go ahead and rewrite some of these things. If you like, let's just go ahead and associate this way. Let's go ahead and just put these two together and use the product rule. That is, we have the sum of logs will now be the log of a product. And again, let's remind ourselves, why are these working? Because the bases are the same. If the bases weren't the same, we couldn't use these rules. So that'll be another thing that we'll contend with when we solve equations. So this will be the natural log of 2 squared times x to the 5th. And now, if you want, we can go ahead and write the last term as log of 1 over the square root of x plus 7 to get rid of the negative, just to make it look nicer. That way we'll have an expression that will come together more easily. But again, it wouldn't matter. Follow formatting. The formatting is satisfied, an equivalent answer is fine. And so now we have the log and the log in sum, which again we can bring together as the log of a product. And of course, if you like, you can write 2 squared is 4. So we have 4 x to the 5th times 1 over this, which we can just bring into the denominator. So this would give us an expression that is 1 unit. That is, we start with 3 units and we end up with 1. Again, it depends on the context of the problem. So when you do these examples, though they may be dry and pretty much leading nowhere, it's like, oh, what do? I just do problems just because I like math and they don't go anywhere. Well, right now, think of this again as an academic exercise, getting accustomed to using these properties. And then, of course, when this is comfortable, and it probably already is from your college algebra days, we can do some more elaborate problems. So let's move on. Now, what I wanted to do for the next example is just utilize the change of base. Solving equations, the change of base requires us to utilize a particular base. But say that we just have a question where we want to give an approximation. that we're not solving an equation, but we just want an approximation. And let's do an example like that. This will be numeric. So we could say approximate, WebAssign may say approximate to 6 decimals. So if you saw that directive in WebAssign, you would know that you want an approximation of your exact answer. That is, and it tells you the directions. So you just use your standard rounding for 6 decimals. Again, this is a direction for formatting. So here's what we have. The base 2 logarithm of 540. So you're thinking, okay, I've got a Google calculator and it's got the natural log and the base 10 log, and it really shouldn't matter which one I use if I choose one or the other, and that's fine. So that's what we'll do. We'll pick a base and use the change of base. But I want to make a few comments here. We have base 2. So now 2 to the 10th is just 2 to the 5th times 2 to the 5th. That's 32 times 32. And that's a very famous number, 1024. All you computer people who maybe are considering the STEM field of computer science or computer engineering, you know the base 2 is where the computer people live, you know, on and off, binary notation. And so this is all the movies today are about the computer hackers and what they do, and well, good or bad, let's hope that people will use their computer science ability to do good things. But what we can see here is that if we bump down one level of 2 to the 9th, this will just be this divided by 2. So that'll give us a 5, a 1, and a 2. So at least from the standpoint of base 2, we see that 540, that is, this implies that we have 512, which equals 2 to the 9th, as a lower bound of 540. I mean, when we do these calculations, we want to make sure that our result actually makes sense. A lot of times students will say, well, I did my work right, Professor Ron, but WebAssign marked it wrong. Well, if you get an answer that doesn't look right, then check your answer. You don't just, well, that's what the calculator said. Well, that's no good. You always have to check your work. You have to make sure that your work is consistent. And so when you work problems like this and you get some answer that seems to be in left field, then check it. Something's wrong. And WebAssign's not going to say, I'm sorry, or it's okay, I'll give you a green check anyway. We know that's not going to happen. So now we have 2 to the 10th, or 1024. So we would expect, if we apply the logarithm function, which is a increasing function, so it preserves this, apply the logarithm, then the base 2 log of 2 to the 9th is 9. And then we're looking for the base 2 log of 540. And the base 2 logarithm of 2 to the 10th is 10. We expect our answer to be between these two numbers. And of course, closer to 9. But again, this kind of gives you a ballpark figure so that when you do an approximation, you have some way of negotiating whether or not it seems reasonable. So now this is like, okay, this is our thought process. So we'll say thought process. And then we go back here and just decide, okay, well, natural log or base 10 log. Let's use base 10 log since we've been using the natural log. So we'll have base 10 log of 540 divided by the base 10 log of 2. Remember, LOG implies base 10, no subscript base 10. So now if you like, let's go to our Google. So we can do this. We'll do LOG. Notice we have LN and LOG. Use either, doesn't matter. So LOG 540 divided by LOG of 2. Now, once you decide on a logarithm base, you have to use it. You can't mix and match. Of course, that wouldn't work. So this gives us 9.07681559. We'll just write out a string of decimals. And I like the Google calculator, ladies and gentlemen, because it's got great output, easy to see, easy to use. Students are all the time asking me, what's a great online calculator? Well, the Google calculator is fine. And so now let's go back to our desktop. So we're interested in, let's see, we've got 3 here and we've got 3 here. So we'll round the 5 to a 6. So WebAssign would want 9.076816. Again, this is a very pedestrian calculation, but you know, you're thinking, well, maybe I don't have my calculator. I've just got tables of base 10 logarithms. That would work too, take you a little bit longer. But the idea here is the calculator works using infinite series, which are calculus objects. So again, look at this as a means of satisfying the client who needs a decimal. You know, when you can say, well, my mathematical calculations give this for your payment for your new vehicle, and you have an exact answer, and it involves exponential functions and logarithms, and they're like, okay, can you give me a number? Well, then you take out the Google calculator. So your monthly payment will be $789.52 or whatever. That's going to be better for your client. But I'll tell you this, your client will be happy to see your calculations, will be happy to know that you made a good determination, okay? Instead of just, well, come up with some figure and it not be honest. So again, just look at this example as just a means of getting a good approximation, utilizing the change of base for our clients, for our lab partners. Say we're working a science problem and we need a good approximation. Now, that pretty much covers everything that I want to say about utilizing the logarithmic properties and change of base. Now what we want to do is get into the more interesting ideas, which are the equations. Equations are what we do in math. We think, we're always making things simpler. We compute differentials, we find horizontal tangents, we compute areas using Riemann sums and Riemann integrals. We learn about infinite series. Everything we do in math is a journey to simplify. We start out with an object and we simplify it. We unravel it, so to speak, to understand it. That's what we do. Equation solving is just one of the main things that we do in mathematics, and it exemplifies the philosophy of mathematics. That is to simplify through deductive reasoning. So for instance, let's get at the heart of the matter. Why do we even care about these logs and exponents? Well, because they help us do math, and one of the most important things we do in mathematics is solve equations. So let's just start our journey with this. So we have the base 10 logarithm of 3 plus the base 10 logarithm of x minus 4 equals the base 10 logarithm of x. Ladies and gentlemen, if you can't be excited about what you do, if it doesn't mean something to you, then you have to find it. You have to find something that keeps your interest. And STEM is a wonderful field for doing that. But you can't make yourself love STEM. STEM has to be part of you. You can cultivate an interest, but I will tell you this, you will get farther in STEM if you excel in mathematics. That will open doors where before doors would be closed. So spend the time on your math, and you can call the shots. Now, when you look at this equation, in this, we found when we studied polynomials that we got imaginary zeros at times. For the real polynomials, they occurred in complex conjugate pairs. And then there was an example in WebAssign where we had polynomials with imaginary coefficients, which anything goes. Well, when we solve these equations, we're always going to look for real solutions. So we're going to say solve in R. So you won't spend a lot of time with imaginary numbers in the calculus sequence, but when you take more engineering math and complex variables, the imaginary units come back. So now to solve for X, to solve for all real values X, for which this is true, we can start out by combining. That is, use the product rule in reverse. So we have the log of 3, or the base 10 log of 3 times X minus 4 equals the base 10 log of X. Now, of course, this opens the door to another set of circumstances that we need to remember. That is the one-to-one property, of base A exponentials and logarithms. Remember, it's logarithm, not logarithm. Logarithm. That's a strange word. One good thing about mathematics is that the words are so unusual, you can't forget them. So now, remember, if we have A to the X equals A to the Y, by the one-to-one, we know that we can set X equal to Y. And then if we have the base A, and of course, X and Y can take on other characteristics. So base A logarithm of X equals base A logarithm of Y implies X equals Y. Again, one-to-one property. And again, this is the definition that we use in general to show algebraically that a function is one-to-one. And that's not always an easy thing to do. Remember, this is an algebraic or calculus construct. A graph does not tell you a function is one-to-one. A graph doesn't tell you anything. You tell the graph how to be. That is, you know what the graph is because you understand the function. It does not prove anything. And I will say that again because it's going to take some of you that long to believe me. Graphs do not tell you anything about a function. You draw the graph because you understand the function, and that's what you need to understand. Now, at this point, we have the one-to-one property. So now we can set the arguments equal. So equivalently, 3 times X minus 4 equals X. Well, don't we wish all of our equations were this easy? So we have 3X minus 12 equals X. So let's subtract X and add 12. So now if we divide by 2, we get X equals 6. Now, of course, if we're dealing with exponential functions, we don't have to be as worried about checking things, but we just want to make sure that you know, whatever value we get does make sense in the original equation. So the 6 here preserves the positive argument, and the 6 here preserves the positive argument. So this is a valid solution. So we say 6. Now, of course, the idea is just like solving algebraic equations. If we've multiplied, if we've introduced extraneous zeros, we just want to make sure that if we have that, we don't include them, or maybe we just don't have a solution, okay? And we don't want to say we have one when we don't. So we always need to check the arguments of the logarithms to make sure that for that particular value of the variable, they are indeed positive. Now, let's look at another example. So again, what we see here is using the log identity. The sum of a log is the log of a product, and then using one-to-one, we get a real simple solution here. That is, we get an easy solution. Now, let's look at another one. these equations give us ways of understanding these functions in a more in-depth way. Now, again, what we want to do is solve in R, and this is going to give us an opportunity to basically say, okay, do we need any kind of fancy apparatus here? Do we need something more elaborate than what we learned, last lecture? Well, if we look at this, we're thinking, okay, the power of 3 that equals 4 is 5x minus 1. So 5x minus 1 is a power of the base. It's a logarithm. So we can write this in a logarithmic form. That is 5x minus 1 equals the base 3. We know what the base is. It's 3 base 3 logarithm of 4. Okay, well, again, if WebAssign just wants an exact answer, it doesn't matter what base we're using. If we need to change the base to get an approximation, we'll do that. But now we see that in the logarithmic form, we can easily solve for x. So equivalently, 5x is equal to the base 3 logarithm of 4 plus a 1. And now, of course, we can divide by 5 or multiply by 1/5. And this would give us an exact response. So now, of course, this is a number, and then the exponentials don't really care. Any real number will work here. So this is a valid solution. Now, another thing you might think is that maybe WebAssign asked for an approximation. So you wanted to use your Google calculator. You could just change this to the natural base if you wanted. You could say this is just 1/5 natural log of 4 divided by natural log of 3 plus 1. So of course, if you were typing this into WebAssign, either of these would be fine. Now, we don't need to do any elaborate change of base here because this is a very simple equation. And so we just use the definition of the base 3 logarithm. And so now when we write our solution set, we can just use this one, 1/5 the base 3 logarithm of 4 plus a 1. Now, of course, I will always give you questions that you can actually solve. You will find some numerical examples in calculus once you learn Newton's method and some approximation methods that will be useful to you. Some of you may go on to take numerical analysis at the university where you just write computer algorithms to solve equations that have unfortunate solutions. So again, just remember when you solve equations in this class, there are occasions when it'll say, you need a graphing calculator, and I've talked about that. That's just as a prelude to the calculus. But the questions that I'll ask you to do, if you will be able to get an exact answer, and the only approximation would be that you would do this approximation with your Google calculator. So that would be the only time that you would need that. So rest assured that your techniques will be things that are valid based upon the techniques that I've taught you. Now, one example that comes up often, and it's kind of going to be a prelude to the last problem we do today, is a form that we learned back in college algebra. We have 3 to the 4x minus 3 to the 2x minus 6 equals 0. So when you look at something like this, this reminds you of this, but we've got a lot of exponential terms and we really can't combine them. They're distinct powers. But what we're noticing here is that this is basically the square of 3 to the 2x. So we can then say, okay, well, this is 3 to the 2x quantity squared if we use the laws of exponents, minus 3 to the 2x minus 6. So when we look at this equation, we think, oh, okay, well, this is what we spent our lives studying. These are quadratic. We have a constant term, we have a non-squared term, And then we have a square term. So we say this is quadratic in 3 to the 2x. So again, we're happy when we have quadratic equations because we understand quadratic equations. So now we've got this shadow 1 here, we have a -1 here, and a -6 is a constant term. But now we're thinking that factors. So if we do AC, we get 1 times the -6. Well, of course, we don't really care about that. We need to get a -1, so we've got a -6, which we can write as a -3 times a 2. And if we sum those two factors, we do get a -1. So AC method works. So now, equivalently, and of course the leading coefficient is 1, so that's the best of both worlds. So now we have 3 to the 2x minus 3 times 3 to the 2x plus a 2. And that equals 0. So we didn't really, we haven't used anything new. Well, we have used something new. We've used the laws of exponents, and we're recognizing that we've got, exponential terms, but this process was old technique, but not old that it's not good, old that we rely upon it. So now by the zero product, we can set each of these factors to 0. So this will be 3 to the 2x minus 3 equals 0. So that means we can transpose the 3 to get that. And then, of course, we can transpose the 2 to get a -2. So now, first, and one of the many properties that we know of the exponential functions is that they're positive. 3 to the 2x will have a positive output. Again, we have changed the horizontal disposition of this function by making it more compressed. We replaced x with 2x, where 2 is bigger than 1. So again, same song and dance with function transformations, but exponential functions are never negative. So we say no real solution here. So that's always a sigh of relief. I mean, it's not that we don't want there to be a solution, but that's not going to give us any real solution. And then, of course, here we're thinking, well, how simple is this? We just have 3 to the 2x equal 3 to the 1. So the bases are the same. So this would just be equivalent to 2x equals 1. And so x is 1/2. So in some cases, you could look at this and just solve this in your head. Again, the idea here is that if you look at any equation long enough that has fairly straightforward zeros, you can probably pick them out. But we want to make sure that we catch all of them. So now the 1/2 will be our solution set. The idea is that we want to be ready with this technique, especially if it doesn't factor with AC, we've got to use the quadratic formula. And then we will do the same negotiation. We may decide that one of the signs of the radical does not make sense. That is, we get something like this, and we say, well, we discard this because this will not give us a real solution. So lots of the properties that we know about these new functions basically determine how we solve equations. So they are extremely important, very important. Now, the next type of equation that I want to look at, and I would say this, when it comes to solving equations, once you develop a technique, say for instance, you know how to use the quadratic formula. You learn it, you get good at doing it, you practice it to maintain your skills. But what I want to try to do is to give you enough variety with the equations so that if you see something that looks a little bit different, it won't matter. You'll know what to do. You'll know how to combine things or to use the definition of logarithm. So here's an example that I find to be kind of interesting in this class. That is, we have, and again, I've been using a lot of base 2, but we're trying to keep the numbers reasonable. So we've got the base 2 logarithm of the base 3 logarithm of x equals 4. Now, a lot of times in the WebAssign, there'll be a hint if the equations get a little bit more difficult. Sometimes WebAssign will give you a hint, and it doesn't mean that it's the only way to do it. They're thinking, well, try this if you haven't come up with anything that you think will work. So, but this is not one of them. But I do know this: when I looked at this problem, they want an answer that's exact, but they will not take an answer as an exponent, which is interesting. You know, when you click the box, if the little math palette comes out, then that means you can use the symbolic, basically the symbolic whereabouts of WebAssign. That is, you can use the symbolic tools to write the symbolic answer. If it doesn't come out, then you've got to write an exact number. For instance, they didn't say approximate, you've got to write an exact number. And so you can't do 3 caret some number, it won't take it. Because if it wants it to be symbolic, the math pad will come out. So I notice these things when I look at the problems that I've assigned and as I write my own problems. So when you look at this, we're thinking, all right, well, what does this mean? We've got the base 2 logarithm of the base 3 logarithm of x equals 4. So notice here, we see the power of 2 that equals the base 3 logarithm of x is 4. That is, the argument of the logarithm is a logarithm, but it doesn't change how we interpret the logarithm. So the power of 2 that equals the base 3 logarithm of x is 4. So the base 3 logarithm of x equals 2 to the 4th power. And we're thinking, well, interesting. Okay, so 2 to the 4th is 16, right? So now we're just do the same thing again. What's a logarithm? It's the power of the base. So now this says the power of 3 that equals x is 16. So we can write that down. That is, in this particular case, x equals 3 to the 16. And this is why I spoke about what I did before. You're thinking, why is he getting off on this tangent and talking about WebAssign? Well, WebAssign doesn't want this form of the answer. They want the number. And I thought, well, that's a large number. So what I thought about was, okay, well, this is what? If you think about this, we can break it up into smaller pieces. We could say 3 to the 4th raised to the 4th power. The 4 times 4 giving us the 16. So basically this would be 81. 3 to the 4th we know is 81, 9 times 9. And so we could say, well, this would be 80 plus 1 squared times 80 plus 1. So if we were doing this by hand, we could do this. There'll be a point where we can use the Google calculator, but I thought this was interesting. So now what is this? What is 80 plus 1 squared? So that'll be what? 64 with 2 zeros. And then 1 times 80 is 80, times 2 is 160. And then 1 squared is 1. Well, not difficult. 6400 plus 161. So this will give us a 1, a 6, 1 and a 4 is a 5, and then a 6. So 6561. So 3 to the 16 equals 6561 times 6561. So you get the drift. But say you're on an exam and you're thinking, well, Professor Ron, I like to do the computation. I mean, my Calculus 2 students don't have much of a choice, but this is all exact computation. So you're thinking, okay, well, I've done my due diligence. So let's run over to use our free Google calculator and say, okay, well, 6, 5, 6, 1. And we want to square it. So we'll hit the power key and then the 2. I told you this was a big number. 43,046,721, which of course you would get if you multiplied these, even by the Professor Ron approach. It's doable. So we've got 43046,721. That's what WebAssign wants. Now here's the thing, and this is why I actually computed this by hand. If you've got a computing device that's limited, then you're going to get a string of decimals. That's no good. You must give an exact answer. That's why I'm thinking, okay, well, the students might want to just enter this. It was not allowed. So you have to give the exact number. So that's why I like using the Google calculator, because it will give you the exact response without decimals. Because a lot of times you'll get scientific notation and a decimal portion. They, you know, when you do your scientific notation, you've got the power part and the decimal portion, like, you know, Avogadro's number. That will not work. So just make sure, if there are no formatting suggestions about an approximation and the math palette doesn't come out, you need an exact number. So be aware of that. So don't send me messages saying WebAssign is being mean to me. No, WebAssign's not being mean to you. You give them what they ask for, okay? Now, you know, when it comes to doing mathematics, it's like Bach used to say about his compositions. He says, just play the right note at the right time. and in math, we just say, well, just, you know, just write the right letter and the right number in the exact sequence and you'll never have an issue. Well, we know it's not that easy. And I'm not taking the philosophy of Bach here. I'm just saying that before you get upset about something, do some research and make sure that you're satisfying the requirements. So there we have it. Now, one thing that's interesting is that we did some interest calculations last class. And I want to go back to that, but now use our newfound solution techniques to move the problem to the next level. And then there's some good examples in the WebAssign I want you to do. Always go for the exact answer and then approximate it if WebAssign asks for that. So what we're going to do is invest $5,000, $5,000 at 8.5% compounded quarterly. And here's what WebAssign asks you to do. A, compute the amount in 3 years. Compute the amount in 3 years. And then part B, again, we know how to do this from the last class, but we're going to use part B to solve part A to solve part B. And then we want the time to triple. During these COVID times, investments are not doing very well. My investments go up one day and then they plummet the next day, but that's okay. We're in very unsecure times, very strange times. So if I get some gains, I know I'm going to lose them the next week, but that's okay. I can't expect any better. As things improve, the market will improve. It's just a sign of the times. And the thing is, you don't bail out, you weather it. So maybe we'll have to know that maybe our calculations won't be as good here. Maybe we won't be able to depend on them because the market will change. But let's go ahead and do this problem. Now, 8.5%, so we want exact and then ready for approximation. So this will be 8.5%. So what, 17/2%, or 17/200 as a number, divide by 100. So now amount will be 5,000, and we want a nice number for, or at least an exact number for the exponential part. Remember, we have 1 plus R 17/200. Now, of course, we have T equals 3, and quarterly means N is equal to 4. So interest is levied 4 times per year. So we have a 4 here. And then, of course, we get N times 3, 4 times 3. So this will be 5,000. So we have 1 plus, okay, 200 times 4 is 800. So we get 17/800 to the 12th. And now, of course, we just add 800, getting a common denominator, add 817. So we get our base, 817/800. And then, of course, this would require the binomial theorem. So that's exact. When I get comments, again, you know, WebAssign's marking this wrong, it's because you've got round off error. So there should be no error in your calculation until you step to the calculator for an approximation. You should have exact here. And if not, don't be surprised that the round off will cause you to miss the problem. Again, this is how I'm teaching you, and this is what I want you to do. Now, we think, okay, well, what does WebAssign say? If I read here, it says that WebAssign wants to the nearest cent. So with the Google calculator, so let's clear this out. So we're going to have 5,000 times, and this is where the calculus comes in, the binomial theorem, 817 divided by 800, close, and then we use our exponent 1, 2. So the calculus is working for us. So this gives us 6,435, and we'll do 0.931. So we'll round to the nearest cent. That will give us $6,435.09. So again, you will never ever have to worry, and this is going to be the same thing with the applications we do next week. We will get an exact answer, and then at the very end, you approximate it, and you will never ever have to worry about getting the answer wrong unless you just did something here, and that's unfortunate. But let that be the case and not something that you did just because you did refuse to do these calculations. Now the part B, we can actually use what we have here. It says time to triple. So let the principal just be represented with a principal of 5,000 be represented by P. So now triple P is 3P. So this says 3P equals P, and we have our base, our unfortunate base, 817 divided by 800. And now remember, N is 4, but we don't know what T is, so we've got 4T. So we want to solve for T. So again, you know, you're thinking, well, that's a base, but we don't want to use that base. I mean, we'll just use our power rule with maybe the natural log, just no problem with that. when it's convenient, we can use bases here, but that's not a number that we really need to focus on. So we're not going to have base 817 divided by 800. Notice the p's absorbed, so we have 817 over 800 to the 4t equals 3. Now, what I want to do here, instead of using this base, I'll just use a natural log just to get the 4t down to the coefficient status. So this will be 4t natural log of 817 divided by 800. Remember, when you take the natural log here, the 4t becomes a factor. So it runs from here to here, and we have the log of the base. And then, of course, on the other side, we have natural log 3. Now, why am I using natural log? Because my Google calculator has natural log. You could use base 10 log, okay? I guess it really doesn't matter. Just whichever base that you're going to use. If you're using the Google calculator, you can use ln or log. And now we can solve for t because we just have t multiplied by the number 4 and that number right there. So we have t equals ln of 3 divided by 4 times the natural log of 817 divided by 800. So there's an exact time for the tripling. That is the natural log of 3 divided by 4 times the natural log of 817 divided by 800. That's the exact time. Let's say you've got a client at the bank and they're like, okay, sir or ma'am, I need a number. Can you give me a number? So you say, well, that's right. That's why they pay us the big bucks. We'll go and get you a number. And so we'll go to our Google calculator and we'll use natural log of 3. Then we'll divide, use our parenthesis, and we have 4 times natural log, and then we'll have 817. This is a real easy calculator to use. If you have a Wacom tablet or something, you can use that. I mean, I'm just using the mouse here. Well, that's what a tablet is, but it's easier. But my tablet, I've grown very fond of my document cam, so I like it. So now we get 13. Well, this is not a good investment, ladies and gentlemen. 13 years, that's pretty grim. Of course, we would use some other method to make money quicker. So we have 13,06169. And then let's see what WebAssign wants. They want 2 decimals. So this would give us 13.06 years. Of course, this is an academic exercise. If you had to wait that long, it'd be better to ask a friend and pay them back. The thing is that as you all maybe have the opportunity to study some finance, when you make investments, they're in the form of annuities, and annuities have gotten a really bad rap lately. But if you want to make money quicker, you've got to do periodic payments, not just a payment, one lump sum payment. So I guess if you had plenty of time and you weren't worried about anything and you had other sources of income, this is fine. I mean, this would be like a slush fund. This would be like, okay, well, this is just extra money, and it's a secure investment. Maybe the banker says, okay, you won't have to worry about the market taking this money from you. You make this investment, it's secure. And so maybe that'll be a good way to make money. Of course, if you're doing the annuities, you're like Professor Ron, it's the up and down of the market, and it's not always the best. But when the payoff is good, that's it. How much risk you're willing to take is really the name of the game. The higher the risk, the higher your output can be, but also the more you lose too. So that's just the nature of the investment. And it's all mathematical, isn't it? And then of course, some of you may go on to study more economics and work in the finance field. That's another STEM career. that would be very, very rewarding. So I've had many students who have ended up in finance that thought they wanted to be engineers, and I thought, well, that's great. It's a wonderful, rewarding field. Now, let's look at this. Let's do an inequality. Now, of course, again, the key is use the identities and the definition of logarithm to get an exact answer. And say, for instance, you know, we had something like this. Do we use the techniques that we already know about inequalities? And the answer is yes. So say we're asked to solve this inequality. That is, we have x squared times e to the x minus 3 times e to the x. And again, solve in R. So again, you look at this particular problem and say, well, this is a good problem because I already have a 0 here, and I can clearly factor this. Now, again, once we factor it, we look for BVs, and then we just do a sign analysis. If we can use the multiplicities to quicken the process, we do. That's something that I've tried to make you aware of if you feel comfortable with it. So now notice we can factor e to the x out of each of these terms. So equivalently, e to the x. And another thing, I'm getting all these questions from you. It's like WebAssign doesn't like my factorization. Ladies and gentlemen, complete factorization means you factor everything. Some of you are finding all the zeros and then you refuse to write them in the factorization. You can't leave a quadratic in the factorization. It must be linearized. They must have all x minus c1, x minus c2. You have to do that. That's when they say complete factorization, that's what they mean. So please don't make that error. If you did all the work to get the zeros, then you're already home. You just have to say x minus that number, x minus that number. So be careful with that so that you get rewarded for all the work you've done. Now, of course, we want complete factorization. This is a difference of two squares. So we have e to the x, and then we have x minus the square root of 3, and x plus the square root of 3. Now, of course, when we do our complete factorization, we'll say minus a negative just so we can expose the actual c. But now we see that this factorization gives us all the BVs that we're going to have. Notice each of these factors would be something we'd analyze. Well, we're now back to this e to the x. E to the x is never 0. That's always positive. So we have e to the x is never 0. So we're not surprised what that gives us. Or we've got what? X equals square root of 3. That is for the BVs. And then we have or x equals negative square root of 3. So I've kind of solved it and written the BVs at the same time. So that was, you know, really what we're doing here is we say we solve this equation to get this, we solve this factor to get this, and then the BVs would be here and here. So I could just say, let me just erase this. Here's our analysis. Be consistent with what I've been doing. So BVs would be square root 3 and negative square root 3. Okay, so we just think, okay, this is degree 1 in the sense, or multiplicity 1 copy. What's the repetition? What's the repetition of square root of 3? 1. What's the multiplicity? 1. What's the repetition of negative square root of 3? 1. Multiplicity 1. So now we have negative root 3. We have positive root 3. So again, you can take a number over here because we'll be able to use the multiplicities. So like we have a negative 10, right? So now if we put in the negative 10, this is always positive. So we have a negative. And then a negative 10 here, we're still negative. So we get positive. And now, of course, these have multiplicity 1. So we've got to cross and then cross back up. Of course, these are not vertical asymptotes, so we don't have to worry about that. So now we have negative here, and plus here using the multiplicity. And then of course the square roots, they don't get checks because of the fact that we don't want 0. So the only check we have is there. You put x's here if you want. I won't do it. Sometimes it's probably best just to put the checks and follow the checks. But if you want to put an x there, an x there clearly is not negative in these regions. So this implies that x will live between the negative square root of 3 and the positive square root of 3. So just looking at this, you don't have to worry that you don't know how to do it. You do know how to do it. The only additional piece of analysis was just recognizing the fact that this is never 0, it's always positive. And so that's an attribute of the exponential function, which we will use over and over. So yes, the beauty of a lot of these functions is that they have some real simple characteristics. We just have to remind ourselves of them so that we don't slip and make careless mistakes. Okay, so a nice example, but not a very hard example. Now, there are a couple of examples here before we get to the last equation, which actually allude to a problem that I talked about yesterday. What I want to do is maybe an example where we have to change the base, not because we're doing an approximation, but because we're trying to solve an equation. So look at this example. We have the base 3 logarithm of x plus the base 9 logarithm of x plus the base 27 logarithm of x equals 11. So the idea here is that as we do a problem, you can do an extra problem yourself and make up a problem in that similar nature to give yourself additional practice. The nice thing about solving equations is that if you need another equation, you know, you can check in your ebook, or you can just make one up. The idea is that the practice that you get in making one up and then seeing if you actually get a solution is a good one. Now, when we look at this particular problem, the first thing we would like to do is say, well, let's combine all of these logarithms, but we can't do it because the bases are not the same. They're not aligned. So when we do these identities, we're assuming the base A logarithm for each term. Now, of course, what I'm going to suggest here is not unique. What I'm going to suggest is just easy. So notice here, we have 3 different bases, but all of these bases are powers of 3. So maybe we'll just leave the 3 here alone and convert these to convert these to base 3. So we'll just say convert all bases to 3. So that just means that we'll leave this one alone and change this one and change this one. Again, not difficult because these are already powers of 3. So we have the log base 3 of x plus, now we'll do the cosmetic log base 3 of x, and then divide by the base 3 logarithm of 9. Again, that's the change of base factor. And then we have log base 3 of x divided by the base 3 logarithm of 27. So the reason that I decided to use the base 3 for all of these is that these are easy numbers. What we observe is the base 3 logarithm of 9 equals 2, because 3 to the 2 equals 9, and the base 3 logarithm of 27 is 3, because 3 to the 3 equals 27. So those are easy numbers. Again, this is not unique, but it makes the solution process easier. Rarely are our techniques unique. You know this just because of what we do when it comes to solving these particular equations. So now let's look at this. So what do we get? We have log base 3 of x plus, now again, we're going to just fill in 2 here, log base 3 of x divided by 2 plus There's something. Yeah, there was something on the camera. You could see a little dot on Professor Ron, and I thought, oh, it's on the camera. Ugh, sorry. Log base 3x divided by 3 equals 1. Okay, so now again, how can we combine everything? Well, we have a base 3 log in all of these terms, so we'll factor that. I guess it's come back. I don't know what's causing that. Is it, I don't know if it's there or if it's on, it might be, is it, I don't know. It's right there. Can you see it? Right there? It's kind of weird. So it comes back when I do this, it goes away. I don't know. Maybe I'll have to see if I can get rid of that. So now we factor the base 3 logarithm of x, and this gives us 1 plus 1/2 plus 1/3 equals 11. Now, when we think about this and we think about what we're doing, you think, well, Professor Ron, maybe you should move this over here so it looks like a coefficient of the logarithm. And I will do that. First, what I want to do is go ahead and get a common denominator. So we'll do 6. So we get a 6, and then a 2 into the 6 is a 3. So that gives us a 3. And then, of course, a 3 into the 6 is a 2. And I'll write the log term on the right. So now you can see that this is just a coefficient. So we have this base 3 logarithm of x times this number. So this will give us equivalently, so we got what, 6 plus 5, which is 11. So again, these are easy problems if we simply address what we're doing here in a logical format. That is, as you do these types of problems, what we're trying to do is combine things in a way that's mathematically coherent and then use the definition of the logarithm. So now notice the 11's absorb and we can cross multiply by 6. So the base 3 logarithm of x is just the number 6. So now what we see is we've reduced a lengthy equation or more complicated to something very simple, which is really what we do in mathematics. So now we're thinking, what does this mean? This says, well, the logarithm is a power of the base. So the power of 3 that equals x is 6. So this says x, here's another power of 3. This says x equals 3 to the 6th. But now these are easy powers. 3 to the 6th, that'll just be what, we can write it this way. Let's see, what's the simplest way to do this? Oh yeah, we'll do 3 to the 3 times 3 to the 3. Oh, let's do it this way. This will be even easier. Let's break it up this way. The numbers will be easier. Let's do 3 to the 4 times 3 squared. So this will be 81 times 9. That's easier to multiply. That'll much easier. So that'll be a 9, and a 9 times an 8 is a 72. So we get 729. So now you're thinking, well, since the numbers are so easy, you could probably stare at this for a while and figure it out, but that's not the most efficient way. We want to make sure we get all the zeros. So now we see we have a solution set of 729. And this is, again, what I want to remind you of. Intuition is extremely important in mathematics, but we want to be able to solve the problem so that we cover all the bases, so to speak. So using the change of base technique here allows us to reduce the equation to something very basic. And then by using the definition of the logarithm, then we easily get the answer. And of course here I just separated the powers so it was easy to multiply. Much smaller than the 43,046,000 whatever number that went on forever. But as children of the computer, you all know about big numbers. That's just the life that we live right now. Now, what I wanted to do is cover an example that I introduced yesterday in class, but I said we don't have the machinery to do it. And here is that example. Now, of course, the quadratic form is really our main technique when it comes to doing interesting problems. And then, of course, we saw that the change of base is very important when we want to combine logarithms and things. So look at this example. So we have 3 to the x plus 2 equals 5 to the 2 minus 3x. And we want to solve for, or just solve for x, or solve in R. Again, there will be a way to solve this by the techniques that I've shown you in the class. As you get more advanced and you learn more calculus approximation methods, you can write algorithms and things. A lot of times in your engineering classes, you'll write algorithms to solve equations numerically. Often, depending on what kind of application you're doing, that's a very important operation to be done. So again, as you learn calculus, you will learn some approximation methods. And then, of course, like I say, numerical analysis is a big field in mathematics that appeals to a lot of the computer sides of math majors. Now, when you look at this, the first thing we might want to think is, let's use one-to-one property. But we really can't use that again because we have different bases. So you might be thinking, well, we could just take logarithms of each side and just go that route. And that's certainly a way to do it. You could take natural logarithms and use the power rule. But I want to give you an example of how you can change the base so you can get that practice. But again, when you solve an equation, however you do it, mathematically correct, no problem. WebAssign will give it the thumbs up. So what I want you to do is change base 3 to base 5. So we haven't had an opportunity to make a change of base with the exponential. We've done it with the logarithm. So let's do that. So we're going to have 5, and that will be x plus 2, bring the power down, base 5 logarithm of 3 equals 5, 2 minus 3x. So again, remember, all of these powers are just that. You can use parentheses if you want, just like we have in the Google calculator. But notice when we have 5 raised to the base 5 logarithm of 3 to the x plus 2, the x plus 2 just comes down. So that's just the utilizing the inverse nature of the base 5 logarithm and the base 5 exponential. Nothing, no major theorem there. So again, if we go ahead and change the base, then we can use one-to-one. So this is an alternative way, but this is one way I can share with you, which actually is something you need to be able to do in calculus. You need to be able to change the base for logarithms, and you need to be able to change the base for exponentials. This is an important technique. And so now use one-to-one property. So the one-to-one property says that if you have the same base and the equality of exponential functions, then you can just set the powers equal, like we're doing here. So we have, now we've got x plus 2 times the number, the base 5 logarithm of 3. So this is the power of 5 that equals 3. Of course, that's going to be what? Less than 1, since 3 is clearly less than 5. And this equals 2 minus 3x. So now we just have first degree in x, so we can get all of our x's together. Let's go ahead and multiply these numbers. So we have x times the base 5 logarithm of 3 plus 2 times the base 5 logarithm of 3. So we're seeing, you see why I teach you symbolic calculation, why I do symbolic calculation when I do word problems back at the beginning of the course, because that's all we're doing now. Symbolic calculation is what gets you through calculus, and inability to do it will mean your demise, and I don't want that. I want you to be able to work with numbers. I want you to be able to work with letters in a very confident way, because that will make your study of the calculus much more easy and much more rewarding. So now we're thinking, okay, let's get all the x's together and the non-x's on the other side. So this will be x times the base 5 logarithm of 3 plus 3x equals 2 minus 2 times the base 5 logarithm of 3. Now, of course, you're thinking, well, there's a 2 in both of these, so I could factor the 2. Well, let's just do it. I mean, factor everything to death. It doesn't matter. And of course, if you needed to change the base to ln or log to get an approximation, you can easily do that. So now the x's we can factor. So this will be the base 5 logarithm of 3 plus 3. And this equals 2 times 1 minus the base 5 logarithm of 3. So now we just have a number times x. So that's like a number times x equals a number. So how do we solve for x? We divide by this number. So we have x equals 2 times 1 minus the base 5 logarithm of 3 divided by the base 5 logarithm of 3 plus 3. Now, the idea here is that you factor when you know you can factor, but do not do any changes to the terms here if you're not positive about the validity of it. Leave it alone. So now notice we have this number here, which we can approximate if we need to, but now, again, we've got a real number that will make sense in this exponential equation, and we simply put it in our solution set. So base 5 logarithm of 3 plus 3. And of course, if you need to approximate the base 5 logarithm of 3, if natural, exponential, so you could just, so base 5 logarithm of 3 equals natural log of 3 divided by natural log of 5. So you could just replace this term with this, and you're good to go. So this would be an approximation of the base 5 logarithm of 3 using the natural exponential. So again, remember, all of your calculations are exact. And then you can get a nice approximation if WebAssign requests it. Again, the key here is exact calculation, symbolic computation, until we get to the point to where either we're done or an approximation is requested. Now, one thing that you're going to do in your calculus class at the end, if you have Professor Ron, I know that I use the Larson calculus text, and there's a very nice section. We actually do inverse trig functions calculus in Cal 2. So there's a nice section at the end of chapter 5 that covers hyperbolic functions and the inverse hyperbolic. And so these are functions that are used widely in physics, mathematics, and engineering. And so the hyperbolic sign actually is a function that is written in terms of the natural exponential, and it looks like this. Here's an example. We have y equals e to the x minus e to the negative x divided by 2. So this is actually what you call the hyperbolic sign. It's not the sine function from trigonometry, the standard trig. This expression here, e to the x minus e to the negative x divided by 2, is given the name hyperbolic sine, and the notation would be sine with an hx. So don't worry so much about that. That's just what this is. But this is the translation of that. So this is what we're going to focus on. And here's what I want you to do. I want you to solve y equals e. That's kind of strange. I just made this up, but it gives you a good example of what you need to be able to do when you want to convert equations to quadratic form in order to solve them. So maybe in WebAssign, so WebAssign might have written the problem just like this, and maybe I'll put this, put this in myself as an extra problem. So basically WebAssign could say solve. I've written it here, but that just means e to the x minus e to the negative x over 2 equals e. So the equation could have just been written this way. And then you say, okay, well, I'll cross multiply and put all the terms on one side and see what I can do with it. So here's an equation to solve. And let me give you some advice as to the type of technique which can be very useful to you. And it will also cover a type of equation that we've done today. So equivalently, we have e to the x minus e to the negative x equals 2e. Now, if you like, let's put everything on one side of the equation. So e to the x minus e to the negative x minus 2e equals 0. Now, you look at this and think, well, I could see trying to convert this into a quadratic form. Now, this is a common technique in mathematics where we multiply by a convenient one. We do it in calculus and analysis all the time. That is, we can possibly introduce other zeros, but if there's zeros of this, it will help us to uncover the legitimate solutions. And so this technique may give us more than we want, but it will certainly uncover what we want if that what we want actually exists. So we'll say multiply by e to the x. This is basically how you solve for the inverse hyperbolic secant function. So we're doing an inverse procedure that is kind of shrouded in solving an equation. So let's multiply by e to the x. So everything gets hit with an e to the x. So we get e to the x times e to the x minus e to the x times e to the negative x minus 2, I'll just put the 2e and then the e to the x. So it looks a little nicer. Okay, now we want to use the laws of exponents. So e to the x times e to the x is e to the 2x. That's a squared term. And then here, well, look, this is minus 2e times e to the x, so we'll put that second. So the minus 2e is the coefficient of e to the x. That's the squared term, and that's just got a 1 out front. So it's like quadratic so far. And then, of course, x plus negative x, using the laws of exponents, is 0. So e to the 0 is 1. So we just get minus 1 here. So now we have converted our equation into a quadratic in e to the x. So this is a standard technique, quadratic in e to the x. I actually did this one, this technique as a freshman at Carolina when we used the Earl W. Swakowski calculus text. Swakowski was a professor emeritus from Marquette University, and his text in calculus was as famous as the Larson text is now. It was the calculus text. And then, of course, his, ran its run, whatever. And then the Larson text came along with the Stewart text. Dr. Stewart who has written this pre-calculus book, also has a very fine calculus book, which I used as a TA at Texas A&M University. But I'm a little bit more fond of the Larson text, which I use here at San Jac, basically because I don't know, Dr. Larson is a topologist, and I like the mathematical pursuits that he uses in his book, even though the Stewart text is excellent. I guess I just, having used it, I like it more, and there are things about it that are good. So the idea is that these are true and tried techniques. So now this is quadratic in e to the x, but clearly the AC method, that'll give us -1. That's never going to add to -2e, so we have no chance of factoring this. So now we're going to use the discriminant. So b squared minus 4ac. So we have -2e as the b, so -2e squared minus 4. And then, of course, we have the 1, the a, times a 1. And then the constant term is -1. So now we have 4e squared minus minus plus 4. And of course, we can factor the 4, so we get 4 times e squared plus 1. So now there's the discriminant. So now we've got what? Quadratic in e to the x. So e to the x equals the opposite of b, which is 2e, plus or minus the square root of the discriminant. Now the square root of 4 is 2, and then the other stuff just stays under the radical, e squared plus 1. That is not a perfect square. Divided by 2a, 2a is 2 times 1, or 2. So now we see that all the 2's absorb. So if you can convert something to quadratic form, then you have opened the door to a solution, because there's nothing about the quadratic equation that you don't know. So any technique that produces a quadratic equation is a good technique and is something that you will rely upon heavily. So now we have e plus or minus the square root of e squared plus 1. Now, this is where we get to use, again, the same strategy that we've utilized 2 or 3 times in the lecture today. E to the x is positive. Now, the square root of e squared plus 1 is larger than e, obviously larger than e. And so the negative here would produce an output here that's negative. So we discard the negative radical, since e to the x is positive. So the mathematics is selected for us here. When we have the plus or minus, the mathematics of this problem selects the positive square root. So this implies that e to the x actually equals e plus the square root of e squared plus 1. And so now, what do we have? Well, what's the logarithm? It's the power of the base. So the power of e that equals this number is x. So x is a base e logarithm. X is the power of the base. So equivalently, x equals the natural log of e plus the square root of e squared plus 1. So now, just using the construct of creating a quadratic equation, we've actually found a solution to this equation. So again, it does not matter when you start to solve an equation, there may be a very simple way to affect a solution. However, when we cross multiplied and retired everything to one side, we thought, would it be convenient to make this quadratic? So we try this technique. And of course, it introduced a solution that made no sense, but the other one did. So we found the solution by using this algebraic technique. And so now when we look at this particular equation, we see symbolically that the value for x is the natural log of the natural base plus the square root of e squared plus 1. So again, exact. And then, of course, if you wanted to use your Google calculator, you could get an approximation of this. So the beauty of the techniques that we're seeing today, we do not leave anything behind. We think about our symbolic computation in week 1. We think about our BV technique. We think about all of the quadratic equation theory, the function theory, working with quadratic functions. We use everything that we have already learned to apply to the base A exponentials and the base A logarithms. So what we're seeing here is that as we work through these problems, we don't leave anything behind. We add to what we already know, and then we can see that everything that we're doing is building to the ultimate goal of successful transference through the calculus sequence. A successful study of the calculus sequence will prepare you for anything. That is, you can go on and become an engineer. You can go on and become a math major and study topology and advanced calculus and number theory and numerical analysis, combinatorics, probability, Galois theory. There's so many things in mathematics. You can say, well, I'm going to do computer science, so I'm going to learn more about discrete math and write new algorithms for Google. Okay, I mean the opportunities are endless. So just remember, once we complete this, we're going to move into the trigonometry, which is going to be a lot different, but we're going to bring along all of the techniques that we've been using. Nothing will ever get left behind. We may not use everything, but it will always come back in some shape or form that we'll have to use. So go ahead and get busy completing the sections on the logarithms and exponentials. And then next week, we will do some applications with the instantaneous growth and decay and the Newton law of cooling. And once we complete that, then we're going to be ready for trigonometry and Professor Ron's unit circle. Okay, so thank you for your attendance today. Enjoy your weekend. If I see you at office hours, fine. If not, good studying and have a great day. Bye, everyone.
Bye. Thank you very much.
Bye. Have a good day.
Oh, you all too. Remember, study that math. What your future is what you want to carve in stone. And I want everybody in this class to have a great future. You have great attitudes. You work hard.
Thank you.
You love math. I mean, I think all of you all love to learn. You're very positive. And that is one of the best attributes to have. And share this with your friends. If you have friends that are depressed because of the situation, be strong for them and help them to get through this. This is a tough time, and I admire what you all are doing. So keep it up.
Thank you.
Yes, sir. Thank
Bye.
you. Good day.
Bye.